Okay, welcome to Serverless Days ANZ 2020. I'm extremely excited to be part of this event, and I would like to thank upon the organizers, the community members, the audience, everyone who is involved with this event for the great effort they have put into get this one running. So with that, let me start with my presentations. So today I'm going to talk about serverless deep neural network with Azure Functions and ML.NET. This is the topic of my today's talk, and let's get started. So a brief introduction about myself. I'm a cloud architect at Harman. It's a Samsung company, and the domain I've been working on is a professional audio, video, and control. Area of expertise is cloud and distributed computing. Interest area is artificial intelligence, machine learning, cloud, and IoT. I'm based out of Bangalore, India, and I'm a member of .NET Foundation. So this is a brief agenda about today's topic, today's session. So we are going to cover a little bit on the deep neural network, then a serverless, then a little bit on Azure Functions, then ML.NET, and demo followed by these topics. So I'll just cover a brief about these topics. I'm not going to go deep dive into the topics because each one of them involves a lot of study that is required to have them, and each one is a very comprehensive and have a very deep study involved in it. So let's get started. So we'll start with the deep neural network. So in this, we can say, if you look at the picture given below, we have a lot of things that is revolves around the field of artificial intelligence and data science. And when we say artificial intelligence, it is like a superset uh, of all these things that is present in this diagram, whether it is a machine learning, neural network, or deep learning. So what is artificial intelligence? So artificial intelligence is nothing but it involves a computer executing a task that a human can do. So it is more or less related to the things that a machine can do, which is very much similar to what a human can do. Whereas machine learning is a subset of artificial intelligence. It involves computer learning from its experience and making decision based on the information that is available to it. So what it does is it tries to uh, gather the information, and based on that information it tries to see the pattern that is present in that data, and based on that pattern, based on those patterns that have been evolved as part of the machine learning, it is being utilized to make decisions based on the information that is developed. So this is about machine learning. Now coming to the neural networks. So neural networks are very much similar to what we have in the brain. So we our brain is composed of lot of neurons which coordinate with each other, and which function as a cohesive unit, and it whenever some action is triggered, they get activated, neurons get activated, and based on those activations we get a different output, some output from the neuron, and which is being transmitted to the next neuron, which does the gets activated. So it is a chain of reaction that is happening within the brain as part of the neurons getting triggered and getting activated. So similarly the same thing happens with our neural networks as well, wherein we provide some problem to it. It gets analyzed by these neurons, and which based on the information provided to the algorithm or the network, it activates those neurons, and once those neurons gets activated we get to have some output out of that one, and which is being carried forward to the next neuron. So it is a chain of reaction which allows you to utilize the information that is provided by the previous neuron and being for carried forward to the next neuron. So this is all about the neural network, but how does deep learning is different from a normal machine learning? That's a question that comes to everyone's mind. So machine learning is more of it involves some of the manual tasks that is being done, whereas in deep learning everything is automated, and it the way it differs from the neural networks or the artificial neural networks is it has a high level of a deep level of you can say layers that allows you to make better predictions in a less time compared to an artificial neural network where we only have one layer. So a deep learning involves multiple layers where layers could be of input layer, then followed by multiple hidden layers, and finally the classifying layer, that is the output layer. So that is all about this picture, the deep neural network that we have. Now coming to the difference between the machine learning and deep learning, I already told that some of the for task has been carried out with the manually, whereas in deep learning everything gets automated. For example, if you look at the current picture, you have input being fed to the machine learning algorithm, and we do the feature extraction. So feature extraction is something that is done manually, so it may be done by a artificial intelligence expert or a data scientist, which allows you to get the features, and once the features are extracted it has been passed to for learning the patterns that is hidden in those features. So once we get those features, we give make a prediction out of it, or we make a classification out of that one and give it as a output. So the features could be, for example, if I take example of a car, a car will have a set of wheels, it will have a set of, if it will have a steering, it will have a headlight. So these are kind of features which is being given by the which is being given by the data scientists or the artificial intelligence experts, which extract this information and feed it to the network. Whereas in deep learning, these features, what we call it as tire or steering or headlight, these are all automated. So these all are analyzed by the network itself and fed it into the network for further learning or further classification. So this is a basic difference between a deep neural network and a machine learning. So coming to the serverless, so serverless is computing. It's a cloud-based computing, which allows execution. It's a execution model in which the cloud provider runs the server, and it allows dynamically management of the allocation of machine resources. So for example, you have some code that you want to run, either you set up the whole thing for it. For example, you can whole infrastructure for it. For example, you will set up the virtual machine, you will set up the virtual network or the network settings for it, and you will set up the database. Everything you will be setting up. So but that's a very expensive activity. If you have something very small to be run and that doesn't need the maintenance of these things, so why should we go for that one? So if you look at the diagram here, traditionally all the security aspect, the database aspect has been taken care by the infrastructure people, and we need to maintain it on our own. But with the advent of serverless, there are plethora of use cases that have evolved, and which involves like delegating these activities to a cloud provider and focusing mainly on the business logic. So it's very fast as well, so time to market is reduced to a great extent, and the cost has been reduced a lot by because here on the pay, the you are going to pay only for the usage, and you are not going to pay for the idle time of execution. So for example, if your function, if your code is not executing, you're not going to pay anything for that one, whereas you are only going to pay for the things that is for the code that for the time duration for which your code is running. So it makes it a very good use case for many of the examples. So in for example, the example I'm going to demonstrate is about image classification. So it is about classifying a class within a set of from an image that is being fed to the system. So for example, it will detect if we will fed a image of a dog, then it will detect whether the image contains a dog or what class does it contain. So just for this thing, you need not to set up each and everything like a virtual machine or network settings or a database and all those things. So these can be very easily delegated to a serverless environment. Coming to the Azure functions, so it is a serverless system or technology provided by the platform. It is a serverless platform provided by Microsoft Azure for running your code in the cloud. And basically, what it involves is you have a code that is nothing but your business logic, and it will be triggered based on some event which may have the data. So in our case, the event is you are uploading an image to a server. So here it will be basically a function where you are uploading the image, and the data is acting as a so it data is acting here as image is acting as a data over here, and the code that you have written to classify the image, it is acting as a code part of it. So once you combine these two things, you will get the Azure functions here. It is being triggered by multiple event sources. So in our case, for this example, we am going to use the HTTP trigger, whereas it could be done by multiple sources such as notification hub, event grave, event hub, cosmos db. So there are a lot of triggers that are already available, and you can leverage and get the data out of that one, process it, and give a output. And it will be pretty fast, and it's very easy to scale the Azure functions compared to a server where you need to do either a horizontal scaling or a vertical scaling. Here everything is done automatically. I'll just briefly touch upon the ML.NET part of the system, the thing that I'm going to demonstrate today. So ML.NET is a machine learning framework from Microsoft, specifically focused for Microsoft .NET developers. And it has been released, I think, last year, and it is making a very good progress in terms of the features that is getting added day by day or week by week. And so till now, if you're a .NET developer and you wanted to try something in the field of machine learning or data science, you need to go learn either Python or R, or you need to have a platform such as Azure Machine Learning Studio, or Azure Machine Learning services such as cognitive services, which is based on the subscription from the Azure. So you are totally dependent on those things. Now, coming to this ML.NET. So ML.NET provides you a framework that is you can run locally on your system, and you can try and experiment few things. If you are convinced, okay, things are working fine, then you can push it to any of the platforms such as Azure Web Apps or Azure Functions, or in your VMs as well. So it is nothing more, much more than a library. It is very small library that has a lot of capabilities in it, and for making different type of machine learning algorithms. So you can have a different set of problems being defined, and which can be easily solved with this framework. So these are some attributes of this ML.NET framework. So build your own. So you can build your own custom models by writing C Sharp or F Sharp code. So till now it was available in Azure machine learning through by writing a Python code only, but now you can leverage those things and write your custom models where you need to have more control. Then in that case you can use this machine learning studio. Then it's very much a developer focused. So which what does it mean is ml.net provides just the right amount of productivity and control. So you can write c sharp code, you can normally debug it, and you can play around with that one. It's very extensible. It's has a very compatibility with different machine learning models such as TensorFlow, or the framework such as TensorFlow, PyTorch. So extensible in the sense it provides a common standard such as ONNX, which is Open Network Neural Exchange, wherein you all these platforms give a model in the ONNX format, .onx format, and you leverage that one into your thing. So suppose I have a predefined, someone has created a model which is in pytorch, so I can convert that one, that pt file into .onx file, and we can leverage that one in our ml.net framework. So you need not to create the models from scratch. You can just leverage and you perform the transfer learning out of that one. Next one is proven. So ml.net has been introduced in Microsoft in the year 2002, that is 18 years back. So and it has been extensively used internally within Microsoft in platforms such as Bing, PowerPoint, Excel. So it's kind of a very proven library or a framework that is available now for the public to use. It was open source last year, and current version is 1.5.1. So that means it's making a good progress, and with great features coming up every week. It's last not but the least is the open source and cross-platform support. So it's a cross-platform and open source. That means it can run on any of the platforms that is being provided. It's a good tool to check it out, and we will be leveraging it for image classification problem today. So now image classification. So what is image classification? It's about feeding some data of images, and once those images are being fed to the system, we see that we are feeding it to the network. So what network does is it tries to learn the features out of that one. For example, it tries to learn the features such as uh, car wheels, car headlight, car steering. So these are the different features it try to learn, and based on these features it makes a prediction out of that one in the end, which is we call as a classification. So as you can see here, we are feeding a lot of images of the car, and the network is learning, and based on these features it is making a prediction. Okay, and that is like a probability. Okay, so it's saying that 95% it's a car based on the features it has learned, and 3% it is still saying as a truck or a bicycle. So that way, the reason why we are getting truck and bicycle here is uh, a truck may is also having a set of wheels, and bicycle is also having a set of wheels. So the network is make thinking that it may be a truck as well, it may be a bicycle, but the percentage is very low compared to the percentage that is being predicted for the car. So this looks a very good model wherein you can easily say, okay, like if the threshold, you can set a threshold. Okay, if it is 90% accuracy, then we can say, okay, we will take that probability. So today I'm going to use the transfer learning. I'm not going to train the model from the scratch. The training from scratch is like you feed in the whole set of images, 100 million images or 10 million images to the network, and it learns the features out of that one, and it makes a prediction out of that one, and it generates a model. So model is used for making a prediction. So this whole process is very time consuming, and it may vary from a day, 2 weeks to months. And the computation required is very extensive here. It involves a lot of GPUs compared to a CPU here. So not everyone will have that flexibility of having a high computing power in their systems. So what we do is, so many companies have already trained the models on set on large data sets, and they have shared their model along with the weights that is being discovered after training the models. So MobileNet is one of them. So MobileNet is a very lightweight model that is being utilized within your mobiles to make a image classification. For example, you have take a picture, and the mobile is able to classify what is present inside the picture, whether it's a a cat or a dog or something like that. So it is being utilized in mobiles extensively. uh, the advantage is it's very lightweight. It's around like 13 MB, which I am been using today. And compared to a normal architecture such as LXNet, VGGNet, or other models which are very heavy, such as they are of 180 to 200 MBs megabytes. So like I'll be deploying it to the Azure functions. So in order to keep things very lightweight, I have just used the MobileNet for this tutorial, for this session. So transfer learning is about you have you got the model such as MobileNet. You got the model. Now you utilize that model to make a prediction on your images on your data set. So the thing is that here the data set should be very closely related to the original model on which the training has been done. So if we look at that MobileNet, it has been trained on a uh, ImageNet dataset which comprises of 1,000 classes in it, and each of these classes are represent something within the ecosystem, such as a cat, dog, then car, truck, all those things. And if we are going for today's scenario, we are going to predict a dog, so which is already present in MobileNet. The MobileNet architecture has already learned all these things, so we need not to recreate a model. We need not to retrain the model, and we can save a lot of time and computations on that one. And the transfer learning will be pretty fast compared to normal training which is done on from scratch. So with that, so this is the architecture I'm going to for the application that I have developed today. So this is a user which is nothing but your REST client in today's scenario. So what he will do is he will upload an image to the Azure function, which we have exposed a API such as classify image, and we will be loading a model. So this is the Onyx file, which is nothing but a MobileNet model, which I have stored on the Azure blob. And we will be loading that model to our Azure function. So Azure function will leverage that model and make a prediction. And based on the prediction, it will give you a number. So which is nothing but a class present out of 1,000 classes that is being defined in the ImageNet class. So with that, let's get to the demo. So we are going to create a Azure function app that is already done. Then we need to save a model to the Azure storage blob. Then we need to create a classify image API. We need to load the model in Azure function, make prediction, test through Postman locally first. Then once we are convinced, okay, things are working fine, then we'll just deploy it on cloud in the Azure function. Okay, okay, let me turn to the code. Okay, give me a minute. Okay, so before I jump into the code, I'll just show you. Uh, so, for example, this is my Microsoft Azure Storage Explorer, and you can see here you have the emulator running. I have the Azure storage emulator running. It has some blob container, and one of them is serverless DNN. This is the name of my container, and which I have uploaded this MobileNet Onyx file. So, and if you see here, it is of 13 MB. So the size is pretty small compared to the normal models that we get for image classification. And that is one of the reasons I have chosen this thing. So this is on the local I have. So first we look into the local part of it. Then okay, okay. So this is my code editor for this thing. So if you look at here, so yeah, I have already created my solution which names as serverless DNN. It has a Azure function project. So you have to create a Azure function project. So it will create a default file called as function.cs. So I've just renamed that one to my function name, like classify image. And it has a couple of other files such as image settings. Image settings is like you will be uploading a file of one of the classes that is present in ImageNet, but the problem is those size of those images may vary, and when we train and classify something on the uh, uh, model, it requires to have a specific size. So for example, for MobileNet, it is uh, it has been seen that it takes a image of size 224 by 224 by 3, where 3 represents the color channels, but the size is 224 by 224. So image settings has a record of those things, and I'll show you how we can set the size to 224 by 224. Then local dot settings, it is nothing but it contains your connection string and various variables present in the system. Then model input is it will hold the information about the image that you will upload. And model output, it is something that gives you the score or the prediction of the prediction done by the model. So let's see those things. So first thing is I'll go into the image settings. Yeah, so if you see here, like I have defined it as 224 by 224. So whenever we upload a file, it has to be resized to this dimension for in order for our network to consider this thing. Now coming to local settings.json. So here I have provided the this is the connection string for the Azure blob storage. In case of a local setup, it is using use development storage equal to true. This is my container name. Just I showed you the blob container that I have in my storage blob. Then this is the file that we have uploaded on the Azure blob. Okay. Next is mobile input. So here this represents the size, the image source, which is nothing but your image that you upload. So it holds the information. So it holds the information in a bitmap. And image type attribute tells you, okay, what is the size of the image that you are expecting. So here it will be 224 by 224 that we wanted to have. So it has nothing more than this one, so we just keep this much of information. It's like a placeholder for the image that is being uploaded. Here this represents the score is like it's an array of 1,000 classes, as we are using MobileNet, which has ImageNet dataset, which has 1,000 classes. So when we look into this score, it will hold the values for those 1,000 classes. Now this column name is very important for image classification. The place from where I got it is I have this uh, MobileNet v2 2.70 Onyx file, and there is a utility called as Netron, Netron, which allows you to see the content of this file. So I have already opened it, and if you look at here, yeah. So if you look at here, it has a lot of layers. You can see the architecture of this one. It contains convolution, batch normalization, ReLU. So all of the layers have been defined in that one, and we can say, okay, see, it takes input image of size 224 by 224. Now this is the name of the input, and this is the name of the output that it is giving us. So we need to be very careful with this thing. We have to use this one for our model. So this is the name that I have used here. This is same as that is present there. So it represents, okay, this is the output column name in our model. Now these two are defined. Now we will finally go into our classifying page, wherein, so this is our main function, and here you can see that couple of things to note here. This is the function name that is being exposed. Then here I have provided the authorization level, which is anonymous, so anyone can access it, but based on your requirement you can have a different set of authorization level. And this is basically a HTTP trigger. So once someone hits this URL, that means it will get executed. Okay, and after that, so first what we are going to do is we are going to load the app settings, and from there we will read the container name, we will read the connection string, we will read the model name. So this will hold the information about those things. And next thing is load model from blob storage and save to temp path. So why do we need to save it to a temp path? The reason being, currently the ml.net loads Onyx file from a model path only, or from a file path, and not from the string. So we need to create a temporary path where we can save the model. So this is about just creating a temporary path. The thing is that you need to have a unique thing here, unique ID, just to avoid any repercussions of having a same name next time when you run the function. So once you have the temp path, what we are going to, we read the model from the blob first thing. So here what we are doing, we are just creating a blob container client and getting the blob and converting it into a stream. So this is a very basic thing for like loading a blob from a URL uh, from the storage. So you got the model stream in, we need to save this one as a somewhere on the directory, so that you can access it through the path. So what we are doing, we are just saving it to the path, creating a file and just saving it there. The model is getting saved there. Now once it is done, so this is nothing but your input column name and output column name. So we have data and the other one that I showed in the Netron. Now comes the real magic of the ML context, or the ML.NET. So ML.NET, the first thing that needs to be done is to create a ML context. So ML context is very much similar to your ML DB context, which everything within your ML.NET is done through the ML context. So you create a instance of that one. After that you just create a empty list. It is just to say that what is the schema of the input data that we are going to load for the ML context to understand it. It is in the interest of the ML context knowledge only, that what is the type of the schema uh, that is being loaded. So we are going to load it in terms of the model input. Now the pipeline is something that is very important here, so it does the whole magic here. What we define is we perform different transformations on the input image. For example, we resize the image, then we extract the pixels. So if an image is of not of size 224 by 224, we will resize it using this transformation. So various transformations are done, then we will extract the pixels. So pixels is like in an image is composed of a lot of pixels. So for example, in this case it will be 224 by 224 pixels that will be present, and each pixel value vary between 0 to 255 based on the intensity of the color it is having. Then we need to extract those things from the input image. So that is being done by the extract pixels. Last one is the apply onyx model. So this one is the actual one that loads the model from the file, the .onyx file that we have downloaded and saved into our temporary path. And once this is done, we will just fit it means we will train it. So currently we don't have any data as of now, so it will just create a model with a empty data, so that the model can understand what is the input type, what is the output type of it. Once we have the model ready, then what we are going to do, we are just going to feed it to our network to make a prediction. So first thing is we need to load the image. So request.body will give you the stream for the image that is being uploaded. We will convert it into bitmap and create a input data. So this will act as our input. Now ml.net has something called as a prediction engine, which allows you to make a prediction on a single item. So what we need to do is we need to provide the model which is being utilized to make that prediction, what will be the output input type and the output type. So with this we'll get the prediction engine. So it exposes a predict API where we provide the input is nothing but the image which a user is going to upload. So it makes a prediction out of that one and it gives you a score. So score will hold a list of 1000 classes values. So we will take the max out of it and say which is the predicted value for this one, the closest. So for example, in our case we saw car had 95%, truck has 3%, then bicycle had 2%. So likewise we will get the maximum value and we will say this is the predicted value of, like, predicted class of the from the by the algorithm. And this one just we will return it. Now with that I'll just run it locally first, and I'll put a breakpoint here just to show you, like, score will have 1000 classes in it. Okay, in the meantime it is running, I'll show you the Azure part of it. So this is my the Azure, the same Azure functions I have here. And if you see the function here I have created. Yeah, so I have already deployed it to my Azure function, and here we can see that same thing. And I could show you this also. So this is the file that I have uploaded on Azure blob in the cloud. So the same experience that we have there and here locally and here. So let me build it quickly. Okay, In the meantime, let me, okay, it's coming up. Okay, so this is the endpoint that we have for our function. If I just go on to the postman, so this is the same endpoint. I have the body binary and I have just selected the image of a dog. So if you see it like this, so this is the image of my dog. I'll just hit this URL. Yeah. So if you see here, this array should contain 1,000 elements. Yeah, you can see it is like a 1,000 element array, which each one of them having some value. I'll take the max and get the class out of it. So, yep, here you go. It's 212. So if you look at this one, I've already seen this one. So this is the place you have that 1,000 class mapping, 1,000 classes along with the. So if I search for 212, I'll get English setter, which I search on Google. It's like a dog. It's one of the breed of a dog. It seems to be very correct for the model that we have, very lightweight model. Now the next thing is to deploy it to Azure. So we need not to make any code change, any configuration change here. You just go and right click and publish. That's all. So I've already published it and I just demonstrated it how it is done. So once it is published, you will see it in your Azure function. Then you will see your function app. Then also you just make sure that you should have this file available here. Now I'll just make the same thing with the Azure function. So this is my URL for that, and I'll do the same thing here, and it should give me the same result if everything goes quite well. Cool, it's working. So that's the demonstration part of it. Now I'm going back to my slides. Okay, so these are some custom success user stories for the ML.NET. These are the user stories, success user stories, which are present in some of the production systems being deployed at these by these companies. You can have a look around it and see the use cases of them. I'm just running out of time, so in the interest of time, I'll just move on. And this is a link to my resources. So if you look into this, it will be very similar to, yep. So this is a place where I have put everything. Serverless days in Z 2020. It has a deck link, source code link. The same source code is available here, the same class and everything. You can just go through that one. And references. Then that I'd like to thank you each and everyone involved in this great event, and thanks for joining this one and listening to the talk. Hope to see you soon. With that, I'll just conclude and thank you. Have a great day or good evening or whatever the duration you have at present. Thank you.